Okay, so I want to make a correction to this slide, from the lecture on the 26th, because I'll be needing this equation. And the correction has already been made in the lecture that's posted, but here's the correction. So I'm just going to erase the part that I need to correct and write out afresh. Okay, so what I need to do here is just follow through this argument a little more carefully. Okay, so here's the equation that the normal component of E is discontinuous across the surface because of the charge density on the surface, right? That's what differentiates the region 1 from region 2. There's some charge in between them. Okay, so on this side of the charge, the electric field E2, on that side, E1, it's a surface charge distribution, and the normal components of the electric field are discontinuous, and the discontinuity is given by the surface charge density on the surface, some external, some free charges, right? Um, okay, um, so in here, because the electric field is the negative gradient of the potential, I can then um, insert that in here, right? So the potential itself is continuous, but the electric field, which is the gradient of the potential, is not. And so if I just put this in, there's a negative sign overall, right? Uh, so that'll let me take that over to the other side. And so the electric field I replace by the gradient, um, right, of V2, right, minus the gradient of V1 dot the normal, this normal to the surface, and this is equal to sigma over epsilon naught. But remember, there was this negative sign, so let me just bring it over to this side. Okay, and so this I can also write as the gradient of the potential and the normal component of that. So I can write it as the gradient in the n direction, right? And of course, I'm evaluating this just at the surface. I mean, the V2 and V1 are the values just on one side and the other immediately either side of the surface. And so, and this is also evaluated at the surface, and that's minus sigma over epsilon naught. So this here is the corrected version that we shall use shortly. And one thing I just wanted to emphasize is that uh, it's always best to just carry in your head some simple example, visual example of what's being discussed here. And if you remember, we did talk about um, a spherical surface, right? Spherical charge, spherical shell. So let's just, here's the spherical shell with some charge on it. Spherical shell of charge. And we graphed this in class, right? So let's say here's the electric field and here's the potential. And we've done this graph before. Um, and just recall, so this is the radius r, right? And just recall what we had drawn previously. The electric field, if you remember, it falls off as 1 over r squared. And inside, the electric field is zero because there's no charge enclosed inside any Gaussian surface that you draw there. So you see how the electric field was discontinuous, right? And the potential, on the other hand, was constant inside, and outside it fell off as 1 over r. So what's the main point I'm trying to make here? That you can see that the potential is continuous, but the gradient of the potential, here it's zero and then it's something else. And so the gradient of the potential, which is just the electric field, it has a discontinuity. So, you have the potential outside, that could be V2, potential inside, which is V1, and there you go. There's the discontinuity. Okay, so that's the correction I wanted to make here. All right. And then I will now go to my next recording. I'm going to end this one here and give you another. This video just ends right here. Okay. Talk to you soon.